My senior once told me that most software problems aren't caused by bad code, but by bad decisions made way earlier. And in app development, picking the wrong database is one of those decisions you'll regret long after the code is written. It's easy to think of a database as just a place to dump data, but in reality, it shapes how fast your app runs, how hard it is to scale, and how painful your future refactors will be. So today, we're going to look at 6 different database paradigms, how they actually think about data, and why each one exists in the first place. Let's start with the one nearly every developer meets first: relational database. It is the bread and butter of the industry. Tools like Postgres, MySQL, and SQL Server have been around for decades. This model dates back to the early 1970s and remains one of the most widely used database models in production, with its foundations laid by computer scientist Ted Codd at IBM. He published a seminal paper that introduced the idea of organizing data into relations. You can still find that paper online, and honestly, most of it goes way over my head. But when you skim through it, you can immediately see the sheer amount of math, logic, and formal reasoning behind it. That deep theoretical grounding is a big reason why relational databases are still trusted for critical systems all these years later. A few years after Codd's work, it would inspire the creation of SQL, Structured Query Language, a specialized language designed specifically for reading and writing data in relational systems. But what does relational actually mean in practice? Imagine a car factory. The factory itself is your database. Inside it, you have different storage areas, one for engines, one for wheels, one for frames. Each storage area represents a table, and each individual part inside it is a row. Every part is stamped with a unique serial number, which lets you identify it unambiguously. That serial number is what we call a primary key. Now, when you assemble a car, you don't copy the engine data into the car record. Instead, the car simply points to the engine's serial number, the wheel serial numbers, and so on. These references are foreign keys. They link data across tables. When you want to see the full picture, you run a query that joins everything together. This design keeps data organized in its smallest, cleanest form, a process known as normalization. One of the biggest strengths of relational databases is their reliability. They follow ACID compliance, meaning transactions are atomic, consistent, isolated, and durable. That means if something goes wrong, a server crashes, a network drops, or a request fails halfway through, your data doesn't end up corrupted or half-written. That reliability is why banks, payment systems, and business software still rely heavily on relational databases. The trade-off is rigidity. If your data shape changes frequently or you don't know it up front, constantly altering schemas can slow you down. That's where more flexible paradigms enter the picture: the document database. Systems like MongoDB and Firestore store data as documents, usually in a JSON-like format. Each document is essentially a container for key value pairs, and related documents are grouped together into collections. There's no fixed schema forcing every document to look the same, which means your data can grow and change without constant migrations. You're encouraged to bundle related data together into a single document. Imagine a car dealership app where one document contains everything about a car: its specifications, price history, availability, and even the current owner. When your app needs to display that car, it can fetch one document and be done. No joins, no extra queries, and no stitching data together on the client. This approach makes document databases especially friendly for front-end and mobile developers. Reads tend to be fast. The data shape maps cleanly to objects in code, and your model can evolve naturally as your application grows. They're commonly used for things like content management systems, mobile apps, and early-stage products where requirements are still changing. The trade-off shows up when your data becomes highly connected and frequently updated. If many documents reference each other and change often, you're responsible for keeping those relationships in sync, which can get messy at scale. Document databases shine when your data is mostly self-contained and read-heavy. But once you need extreme speed for very small, frequently accessed pieces of data, there's an even simpler approach. That's where key-value databases come in. They keep their data in memory instead of on disk, which removes the need for slow disk reads on every operation. The database itself is structured almost like a JavaScript object or a Python dictionary. Systems like Redis are built on a simple idea. Every piece of data is stored under a unique key, and that key maps directly to a value. It's essentially a supercharged hash map running on a server. You ask for a key, and you get the value back almost instantly. That simplicity is exactly what makes this model so fast, but it also defines its limits. Because everything lives in memory, the amount of data you can store is constrained, which is why key-value databases are rarely used as a primary data store. Instead, they're usually placed in front of another database to act as a performance booster. Things like session data, cached API responses, and game leaderboards are perfect fits. In practice, Key value stores are most often used as a cache to reduce data latency, and large platforms like Twitter, GitHub, and Snapchat rely on Redis to deliver real-time experiences at scale. But speed alone isn't always enough. Sometimes you don't just want the exact value tied to a key. You want the closest match, the most relevant result, or the thing that feels similar. And that's where vector databases come into play. A vector database works by storing data not as plain text or exact values, but as numerical representations called vectors. These vectors are usually generated by machine learning models that turn things like text, images, or audio into long lists of numbers. Each list captures meaning rather than exact wording. From a code perspective, this often looks like taking a piece of text, running it through an embedding model, and storing the resulting array of numbers alongside an ID or some metadata. Instead of querying by equality, you ask the database to find vectors that are closest to each other in high-dimensional space. Under the hood, vector databases like Pinecone or Weaviate use specialized indexing techniques to make this similarity search fast, even across millions of vectors. Rather than scanning every record, they use algorithms such as approximate nearest neighbor search to quickly narrow down the most relevant matches. This is why vector databases are so important for large language models and AI applications. LLM-powered apps don't just retrieve data, they retrieve context. When a user asks a question, the system converts that question into a vector, searches for the most semantically similar pieces of information, and feeds those results back into the model. That's how features like semantic search and recommendation systems work. And once meaning and similarity matter, relationships between data points also become important, which brings us to graph databases. A graph database stores data as nodes, and the relationships between them as edges. Instead of organizing information into tables or documents, everything is modeled as a network. Each node represents an entity, like a user, product, or location, and each edge represents how those entities are connected. In a graph database like Neo4j, relationships are first-class citizens, meaning they're stored directly in the database, rather than being implied through foreign keys. This changes how you query data. Instead of joining tables, you traverse the graph. A query might start at one node and follow edges outward to find connected nodes based on specific patterns. Graph databases are a natural fit for problems where connections matter more than individual records. They're often used for recommendation engines and fraud detection. The trade-off is that they're more specialized. If your app doesn't heavily rely on relationships, a graph database may be unnecessary complexity. Finally, we have time series databases, which are built for data that changes over time. Instead of treating time as just another field, these databases make timestamps the core of their design. Every data point is written alongside a time value, and records are automatically ordered and indexed by time. This makes it efficient to run queries like "What happened in the last 5 minutes?" or "Show the average value per hour." Databases like InfluxDB and TimescaleDB are optimized for handling massive streams of time-stamped data. Time series databases are commonly used for application monitoring, system metrics, IoT devices, financial metrics, and event logs. They're not designed for complex relationships or transactional workloads, but they excel at tracking trends and answering time-based questions. So which database should you choose? The real answer is that most serious applications don't use just one. They combine multiple paradigms because they are built around different assumptions: a relational database for structure, a document store for flexibility, a key value cache for speed, a vector database for context and meaning, a graph database for relationships, and a time series database for time and metrics. The best developers aren't loyal to tools, they're loyal to outcomes. This was CodeWrap. Drop a like and subscribe for more fast tech explanations like this. Thanks for watching, and I will see you in the next one.